Again, welcome to Data Science using Python. This is Unit 4, Lectures, Exploratory Data Analysis. Again, sometimes a data scientist or data analysis often have a prior knowledge or the prior hypothesis that they would like the data to test. For example, do cell phone users have a higher rate of positive response than internet users? Now, the resulting hypothesis test could be carried out using either classical statistics method or using cross-validation. Because here again, we have the claim or the prior knowledge. So we know in hypothesis testing, we may have the null hypothesis and alternative hypothesis. When we say the null hypothesis, that would be our prior knowledge. So in this case, again, we can use hypothesis testing. Now, when we don't have the prior knowledge, then we cannot use hypothesis testing. So in this case, we can use exploratory data analysis. So here again, we said analysis may have a prior, that's a presupposed by experience hypothesis to test. An example given here also is that its increasing fee structure led to decreasing market share. So here we can use hypothesis testing. Our main goal again is to test the market share, whether it has increased or decreased. So this is more or less a prior knowledge. Now, however, not always we may have a prior notion about the data. That is the prior knowledge. So in this case, we may use exploratory data analysis. And exploratory data analysis, we may come up with if it's a quantitative variables, we may come up with a scatter plot, or if it's a categorical value, we may come up with a bar chart. With these charts, we can find a relationship between the variables. So here we see the approach useful for delving into a data. Most important, again, examine the important interrelationship between the attributes. Identify interesting subset or patterns in the data set. Also discover possible relationship between the predators and target variable. That's if we are doing exploratory data analysis. So the goal here is that if we want to do exploratory data analysis, we may assume there's no any prior knowledge. If there's a prior knowledge, again, the main idea is to do hypothesis testing will be better. So the goal here again is to investigate variable as part of data understanding phase. Is the variables the numeric values or are they nominal or categorical values? Now, if it's a categorical values and I'm going to use a chart, most likely I will use the bar chart or a column chart. If it's a numeric values, I can use a scatter plot, which is best, or histogram. So most important before we start any data analysis, or we can say the main goal of exploratory data analysis is to understand our data. For example, we can find the mean, we can find the median, standard deviation, etc. to summarize. So here we say we should become familiar with the data. Also, we should be able to explore the relationship among the variable set. Also, while performing the exploratory data analysis, we should remain focused on our objective of the project. Here we say, for example, creating a data mining model of a customer likely to shun, or for a customer likely to attract. So if that's our objective. Now, the EDA stands for exploratory data analysis. HT is for hypothesis testing. As we said earlier, the two can be used, but analysis often have a prior hypothesis, then we can use the hypothesis testing. So hypothesis testing could be carried out using classical stat method or cross-validation, as we said. Analysis may not have notions or the prior knowledge about what the data might uncover. In this case, we may prefer to use exploratory data analysis or graphical data analysis. So again, EDA allow users to use graphics to explore the relationship between the predictor variables and the target, or we may say the independent variable and the dependent variable. Also, we can use the graphics and tables to derive new variables that will increase predictive value, or using the binding productively to increase predictive value. So next, how do we use bar in Python? Again, this course is based on Python. So we are going to use Python to create a bar graph with response overlay. Now, bar graph is very good for categorical values. So here we say use bar graph with response overlay. We have two types, either non-normalized bar graph or normalized bar graph. So a normalized bar graph normally will equalize the length of each bar. But non-normalized bar graphs show the distribution of the categorical variables. So again, we can use either the bar graph with response overlay for exploring the relationship between a categorical predictor and also a categorical target variable or a target variable. So what is the best practice for bar graph? We said that when a bar graph with overlay is unclear regarding the response proportion, then we can supplement it with a normalized bar graph. But never provide a normalized bar graph without its non-normalized version. So we should have the normalized version first before. Now, first, how do we construct a bar graph with overlay using Python? So we can, first thing, we're going to import the pandas package. So we import the pandas package as PD. Then we need to get our data. Again, in this example here, we are assuming the data name or the file name is bank marketing training. It's in the C drive. So we use the read underscore CSV to read the file content into a bank train variable. And we have to have the pd.read because we import pandas as PD. Read CSV is in pandas package. So the first thing we do here, we create a contingency table using the crosstab function. So we see again pd.crosstab. This time our data set is in the bank train. So we say bank train, the attribute is previous outcome, and the other attribute is response. Next, we create the bar graph based on the table. So we use the function name plot. Now, when we create a contingency table using the crosstab function, we store the contingency table in a variable name crosstab underscore 01. So to create the bar graph, we use the crosstab underscore 01. So here we say again, crosstab underscore 01 dot plot. So crosstab underscore 01 is our object content. And we are plotting a bar graph. So we say the count equal to bar. And also this bar graph is a stack bar graph. So stack equal to true. Here we say again, the plot function with input can equal to bar will plot a bar graph for us. And also the stack equal to true will specify that the bar graph is a stack bar graph. Now for a normalized version, the table values are proportions of a response, the proportion of the response. So here we have again the crosstab underscore 01, which again is our contingency table. This time we are using the division. Then we sum crosstab underscore 01 dot sum 1 as this is 0. Now what this division function will do for us, or div, it will divide the values of the table by another object within each specified axis, which is specified here. So for example, a crosstab underscore 01 dot sum 1 argument as 1 will sum each row. Then axis equal to 0 means it will divide the rows by these values. So next here we plot again crosstab underscore norm dot plot. because we put our result in crosstab underscore norm. Then we plot it. Again, we are plotting a bar graph again, and it's a stack bar graph. So our result will look something like this. So we have the bar graph. We have also we haven't created our labels yet, which will be, again, the next section we're going to see. So what is a contingency table first? We say a contingency table will help quantify the relationship between a categorical predictor and the target. So we can construct a contingency table, which is a cross-validation of two variables. Now, a contingency table also displays the frequencies for the combination of two categorical variables. So analysis also will refer to the contingency table as the cross tabulation. If you can remember, we use the crosstab function to create it. Also, contingency table will classify the outcome for one variable in rows and the other in columns. Now, these values at the row and the column intersection will be the frequency for each unique combination of the two variables. Again, we will see examples soon. So, for example, here we say, is there a relationship between a gender, male and female? There may be response. So we have response either yes or no, male and female 2 by 2. Or is there a relationship between Mac or PC computers? So this is an example of a contingency table, which is, again, a cross tabulation of the variables. Always have a target variable will represent the row. So our target variable here, our target variable normally represent the outcome, the dependent variable, I would say. So our target variable here is either yes or no. It can be a diagnostic, positive or negative. So yes or no, with the predictor representing the column. So here the predictor variables, which will be the independent variables, we have 3 of them: failure, non-existence, and success. Now, the best practice for contingency table, we say the response variables represent the rows, as we said earlier. Response, again, will be the target variable. Then we need to obtain the column percentage to directly compare the response proportions for each category of the predictor. Next, how do we construct a contingency table using the Python? So here, again, we use the crosstab function. We import the pandas as PD. So we say pd.crosstab. The content of the file we are using is called the bank train, and our response, this will be our response variable, or we say the target variable. And then we also have the bank train previous outcome column. Now here we say for the column proportion, we are going to divide each column by the column sum. So we use the div function again. Remember, the table we create, the contingency table, is in crosstab underscore 2. So we say crosstab underscore 02.div. Then the crosstab underscore 02.sum0. The axis, we make it 1. And we multiply by 100 here means the value will be in percentage. And also we run it to 1. We can see we have a run function here. So run it to 1 means, again, the number of significant digits. Here we say the run function will run the numbers in the table to the specified number of significant digits. Here we specify only 1 digit. Next is histogram with response overlay. Now with histogram, we can use, normally histogram, we create histogram from a frequency distribution table. So here we can say a graphical representation of a frequency distribution table is the histogram. It's the normally frequency distribution. We may have the categories. In this case, will be the age. Then we may have the column, which will be the frequency. So the first category, the first column, the frequency. We may have the relative frequency, cumulative frequency, but with histogram, we only need the category variable that we are checking, and also the frequency for each category. Now, we may have normalized histogram, which will see the distribution of the variable. So this histogram we have here. Now, this will be difficult to ascertain any pattern in the response proportion. But a normalized histogram with response overlay allows us to distinguish the response patterns. But also, it doesn't tell us about the original distribution of age. So this is, again, a normalized histogram. Now, what is the best practice for histogram? Always they say we should use a non-normalized histogram to obtain the original distribution of the data values. Then if needed, we can use a normalized histogram to help better distinguish the response patterns. As we can see in this is a normalized, we can see the patterns very good. Blue represents yes, and orange represents no. Now, how do we construct histograms with overlay using Python? And we are going to import the NumPy package as MP. Again, the name, this is alias MP. It can be any name. Then since we are constructing histogram, we need a matplotlib, which is the package to plot graphs. So here we have the matplotlib.pyplot as PLT. Next thing we do, we want to separate the variables by two values of the variable response. So we go back to where our data is in banktrain file. So we say banktrain.response when it's yes for age, and also banktrain.response when it's no and the age. And we assign the yeses to BTHY, and no to our object, BTHN for no. Next, we are going to create a stack histogram of the two variables. So here we use the PLT, which is again our matplotlib.pyplot package, PLT. Now, if we want to create histogram, we use the function HIST. Then we specify our attributes. So we have BTHY and BTHN. The number of bins will be the number of bars or the columns. So, or categories, we have 10. And this will be a stack. We also include a legend. So the legend can be yes or no. We also include the title of the graph, histogram of age with response overlay. We also include the S label, which is age, and Y label, which is the frequency. And of course, we used peer.show to show it. Then next, again, here we just explain the stack equal to true means we are stacking the variables. Y bins equal to 10 specify the number of bins in the histogram, represent the number of bars. Then the legend, title, S bar, Y bar. Again, let's see how this works. And also the show function will display the figure. And let's go to the previous slide. We can see where. So again, we can see our title here, histogram of age with response overlay. The legend is the response equal to yes, response equal to no, blue and orange. Our x-axis is age, y-axis again frequency. Next, also we can also create histogram with overlay using Python. Here we are going to create either normalized or non-normalized previously. So we would now create the normalized histogram. We save the information generated by the histogram. So we have plt.hist, bthy, bthn. The number of bins again is 10. The stack is true. We assign to n bins and patches. Now we put the information in n into the matrix and obtain the column proportion. So here we say numpy or mp.column stack. N0 and N1, we assign it to N table. Now divide each row by the sum across that row. So we can see N table divided by N table.sum axis 1 and again none. Next, we create an array whose rows are the exact cuts of each bin. And we assign it to our bins variable object. So here we have np.column stack. As we said, the bins are up to 10, so 0 to 10 and 1 to 11. Now we create the normalized histogram by using the BLT again, bar s equal to our bins. We have the height, also the width, and the number of our bins. P2 also will be s equal to our bins. We have the height, 1, width also. Then we have our bin 0, the bottom 0 also. We create our legend. It should be responses yes or responses no. We also create a title, which will be normalized histogram of age with response overlay. We create our S label, which is age, and Y label, which is proportion. And we show it. So here we say the S will specify the bin bounds, and also the height will specify the height of each bar section. The width also will reuse the bar width. So this will be an example of a bar chart. And this is again binding based on predictive value. So we say some algorithms work better with categorical variables. Now, how can we categorize the values of age? So response will be widely vary proportion. The goal of binding is in data science also we use the term discretization. So I may have a values age in quantitative form, a value I can convert to a categorical. So I can say, okay, age, and that's what we have here. If you are between the age of 0 to 27 is 1, 27 to 60 is 2, 30 to 60 up is 3. Now, the good thing about discretizing our variable, it makes the algorithm to run very quick, because now here we have only 3 age differences. Instead of entering any age between 1 to 60, will be too many different ages. So that is the concept we have here now. Now, instead of having the terms, we have only 3 now, because we have under 27, between 27 to 60, and over 60. So binding based on predictive value, here they say the best practice for binding or discretization is to many packages provide automatic binding methods. And if you are interested in enhancing the predictive power of your analysis, always try to use binding based on predictive value. A very good example was the age they gave us. Now, if we are entering age of, let's say, patients, over 1,000 patients between 1 to 70, we may have so many different ages. The algorithm may take a long time to do the prediction. But if we bind it or discretize it, I have over 10,000 patients. Their age category is only 3. So algorithm can work more. Prediction will be more quicker. Now, next is how to perform binding based on predictive value using Python. So here also we import the pandas as PD. Now, bin values normally use the cut function. And the cut function is inside the pandas package. So here we say pd.cut x equal to the bank train age. Now the bins we want 0, 27, 60.01, 100. And this is our binding, but we represent it as a label. We say under 27, from 27 to 60, and over 60. That will be the label. And then the right we assign false. Now what we say here is that S will specify the variables you want to divide. The bins equal to, the bins again will specify the edges of each bin. And labels will specify the bin label. And right equal to false says that we want our bins to exclude the right-hand cut point. This is called exclusion. So we don't want overlapping. Let's say we have from 27 to 80 and from 80 to 90. You can see that 80 will be in two different categories. So that will be the conclusion of these lectures. Again, these lectures give us the idea of using Python. There was no too much theory here, just a few theories, but we focus on how we can use the Python packages, both the pandas and NumPy, and also the matplotlib to do some few exploratory data analysis. So our next lectures will be some examples, which we will post later. Thank you.